Hello, and welcome back to the Cult of Eve ASMR channel. I hope you're having a wonderful day, night, afternoon. And today, I have a real treat for you. We are going to start reading the book, What If? Serious scientific answers to absurd hypothetical questions, which was written by Randall Munroe, who is the creator of the famous xkcd webcomic, which focuses on, really nerdy stuff, science, math, sorts of things, and he has these little, very distinctive little stick figure comics, and it's pretty well known, and this is a book where, as the subtitle would suggest, he offers serious scientific answers to absurd hypothetical questions. And it is a really, really delightful book. I think one of my favorite nonfiction books, if I'm being completely honest, because there's a lot of great nonfiction out there, but this is the sort of nonfiction that I would suggest to someone who normally has trouble with nonfiction, because, if we're being completely honest, there is a lot of nonfiction out there that can be kind of dry, kind of boring, especially if you're not, really, really interested in the subject. But What If is a very fun, very easy read, and it's just very delightful. And I think it's very well suited to this channel. So, let's get into it. And you can see the inside cover has all of these various calculations that have to do with, I think, the various answers in the books. The one that jumps out to me here is 66 tornadoes per year times 1.5 miles times 50 yards over Florida. So that's a lot of fun. What If? By Randall Munroe. I think it was published in 2014. There is a sequel, which just came out in 2022, What If 2, which I also have, and if our little What If miniseries is successful, I will definitely read that one as well, because that was also really excellent. Here is a table of contents for all the various questions, and he does answer quite a few questions, as you can see. And he has a brief little disclaimer: do not try any of this at home. And a brief introduction. This book is a collection of answers to hypothetical questions. These questions were submitted to me through my website, where, in addition to serving as a sort of Dear Abby for mad scientists, I draw xkcd, a stick figure webcomic. I didn't start out making comics. I went to school for physics, and after graduating, I worked on robotics at NASA. I eventually left NASA to draw comics full-time, but my interest in science and math didn't fade. Eventually, it found a new outlet, answering the internet's weird and sometimes worrying questions. This book contains a selection of my favorite answers from my website, plus a bunch of new questions answered here for the first time. I've been using math to try to answer weird questions for as long as I can remember. When I was 5 years old, my mother had a conversation with me that she wrote down and saved in a photo album. When she heard I was writing this book, she found the transcript and sent it to me. Here it is, reproduced verbatim from her 25-year-old sheet of paper. So there's little kid Randall and his mom, Julie. Are there more soft things or hard things in our house? I don't know. How about in the world? I don't know. Well, each house has 3 or 4 pillows, right? Right. And each house has about 15 magnets, right? I guess. So, 15 plus 3 or 4, let's say 4, is 19, right? Right. So there are probably about 3 billion soft things and 5 billion hard things. Well, which one wins? I guess hard things. To this day, I have no idea where I got 3 billion and 5 billion from. Clearly, I didn't really get how numbers worked. My math has gotten a little better over the years, but my reason for doing math is the same as it was when I was 5. I want to answer questions. They say there are no stupid questions. That's obviously wrong. I think my question about hard and soft things, for example, is pretty stupid. But it turns out that trying to thoroughly answer a stupid question can take you to some pretty interesting places. I still don't know whether there are more hard or soft things in the world, but I've learned a lot of other stuff along the way. What follows are my favorite parts of that journey. Randall Munroe. What if? Global windstorm. The question is, what would happen if the Earth and all terrestrial objects suddenly stopped spinning, but the atmosphere retained its velocity? From Andrew Brown. Probably nothing good. His answer, nearly everyone would die. Then things would get interesting. At the equator, the Earth's surface is moving at about 470 meters per second, a little over 1,000 miles per hour, relative to its axis. If the Earth stopped and the air didn't, the result would be a sudden 1,000-mile-per-hour wind. The wind would be highest at the equator, but everyone and everything living between 42 degrees north and 42 degrees south, which includes about 85% of the world's population, would suddenly experience supersonic winds. The highest winds would last for only a few minutes near the surface. Friction with the ground would slow them down. However, those few minutes would be long enough to reduce virtually all human structures to ruins. Here we have a helpful map. In the dark gray, we have where terrible things will happen. And in the very light gray, near the poles, terrible things happen, but more slowly. My home in Boston is far enough north to be just barely outside the supersonic wind zone, but the winds there would still be twice as strong as those in the most powerful tornadoes. Buildings, from sheds to skyscrapers, would be smashed flat, torn from their foundations, and sent tumbling across the landscape. Winds would be lower near the poles, but no human cities are far enough from the equator to escape devastation. Longyearbyen, on the island of Svalbard in Norway, the highest latitude city on the planet, would be devastated by winds equal to those in the planet's strongest tropical cyclones. If you're going to wait it out, one of the best places to do it might be Helsinki, Finland. While its high latitude, above 60 degrees north, wouldn't be enough to keep it from being scoured clean by the winds. The bedrock below Helsinki contains a sophisticated network of tunnels, along with a subterranean shopping mall, hockey rink, swimming complex, and mall. And here we have a little comic. All those years you made fun of us for living in such a cold and dark place. Suckers. And then we have some Finnish, which I won't dare mispronounce. No buildings would be safe. Even structures strong enough to survive the winds would be in trouble. As comedian Ron White said about hurricanes, it's not that the wind is blowing, it's what the wind is blowing. Say you're in a massive bunker made out of some material that can withstand 1,000-mile-per-hour winds. Here he is reading Kid to Sleep. Then the 90-second little pig built a house out of depleted uranium, and the wolf was like, damn. That's good, and you'd be fine, if you were the only one with a bunker. Unfortunately, you probably have neighbors, and if the neighbor upwind of you has a less well-anchored bunker, your bunker will have to withstand a 1,000-mile-per-hour impact by their bunker. That's not good. The human race wouldn't go extinct. Well, not right away. In general, very few people above the surface would survive. The flying debris would pulverize anything that wasn't nuclear hardened. However, a lot of people below the surface of the ground would survive just fine. If you were in a deep basement, or better yet, a subway tunnel, when it happened, you would stand a good chance of surviving. There would be other lucky survivors. The dozens of scientists and staff at the Amundsen Scott Research Station at the South Pole would be safe from the winds. For them, the first sign of trouble would be that the outside world had suddenly gone silent. That would be spooky. The mysterious silence would probably distract them for a while, but eventually someone would notice something even stranger. The sun isn't moving. Oh, the earth must have stopped spinning, destroying everything in a global tempest. I hate it when that happens. I'll kick it and see if it starts again. The air. As the surface winds died down, things would get weirder. The wind blast would translate to a heat blast. Normally, the kinetic energy of rushing wind is small enough to be negligible, but this would not be normal wind. As it tumbled to a turbulent stop, the air would heat up. Over land, this would lead to scorching temperature increases, and, in areas where the air is moist, global thunderstorms. At the same time, wind sweeping over the oceans would churn up and atomize the surface layer of the water. For a while, the ocean would cease to have a surface at all. It would be impossible to tell where the spray ended and the sea began. I can't even picture that. Oceans are cold. Below the thin surface layer, they're fairly uniform 4 degrees Celsius. The tempest would churn up cold water from the depths. The influx of cold spray into superheated air would create a type of weather never before seen on Earth. A roiling mix of wind, spray, fog, and rapid temperature changes. This upwelling would lead to blooms of life as fresh nutrients flooded the upper layers. At the same time, it would lead to huge die-offs of fish, crabs, sea turtles, and animals unable to cope with the influx of low-oxygen water from the depths. Any animal that needs to breathe, such as whales and dolphins, would be hard-pressed to survive in the turbulent sea-air interface. The waves would sweep around the globe, east to west, and every east-facing shore would encounter the largest storm surge in world history. A blinding cloud of sea spray would sweep inland, and behind it, a turbulent, roiling wall of water would advance like a tsunami. In some places, the waves would reach many miles inland. The windstorms would inject huge amounts of dust and debris into the atmosphere. At the same time, a dense blanket of fog would form over the cold ocean surfaces. Normally, this would cause global temperatures to plummet, and they would, at least on one side of the Earth. If the Earth stopped spinning, the normal cycle of day and night would end. The sun wouldn't completely stop moving across the sky, but instead of rising and setting once a day, it would rise and set once a year. Day and night would each be 6 months long, even at the equator. On the day side, the surface would bake under the constant sunlight, while on the night side, the temperature would plummet. Convection on the day side would lead to massive storms in the area directly beneath the sun. With the footnote, although without the Coriolis force, it's anyone's guess which way they would spin. And here's this little guy saying, if the old day-night cycle is gone, when can I feed these gremlins? In some ways, this Earth would resemble one of the tidally locked exoplanets commonly found in a red dwarf star's habitable zone. But a better comparison might be a very early Venus. Due to its rotation, Venus, like our stopped Earth, keeps the same face pointed toward the sun for months at a time. However, its thick atmosphere circulates quite quickly, which results in the day and the night side having about the same temperature. Although the length of the day would change, the length of the month would not. The moon hasn't stopped rotating around the Earth. However, without the Earth's rotation feeding it tidal energy, the moon would stop drifting away from the Earth, as it is currently doing, and would start to slowly drift back toward us. Oh, that might actually not be good. In fact, the moon, our faithful companion, would act to undo the damage Andrew's scenario caused. Oh, it's all Andrew's fault. Right now, the Earth spins faster than the moon, and our tides slow down the Earth's rotation while pushing the moon away from us. If we stopped rotating, the moon would stop drifting away from us. Instead of slowing us down, its tides would accelerate our spin. Quietly, gently, the moon's gravity would tug on our planet, and the Earth would start turning again. And then you have the comic of the moon going around the Earth, going, "Hey Earth, Earth, why'd you stop? Oh no, are you okay? Earth, are you okay? Don't be scared, Earth, I can help. I'm here, Earth, your moon is here. I will never leave you." Oh, that's sweet. That's interesting. The moon would rescue us. Next question. Relativistic baseball. The question is, what would happen if you tried to hit a baseball pitched at 90% of the speed of light? Coming from Ellen McManus. Again, I feel like the answer would be not good. So here we go, before and after. He is throwing, the baseball person is throwing at 80 miles per hour, which is a tiny fraction of the speed of light. And now he's going at 90% the speed of light, which is 604 million miles per hour. The caption says, "Let's set aside the question of how we got the baseball moving that fast. We'll suppose it's a normal pitch, except in the instant the pitcher releases the ball, it magically accelerates to 0.9 c. C stands for the speed of light. From that point onward, everything proceeds according to normal physics. It turns out to be, the answer turns out to be a lot of things, and they all happen very quickly, and it doesn't end well for the batter or the pitcher. I sat down with some physics books, a Nolan Ryan action figure, and a bunch of videotapes of nuclear tests, and tried to sort it all out. What follows is my best guess at a nanosecond by nanosecond portrait. The ball would be going so fast that everything else would be practically stationary. Even the molecules in the air would stand still. Air molecules would vibrate back and forth at a few hundred miles per hour, but the ball would be moving through them at 600 million miles per hour. This means that as far as the ball is concerned, they would just be hanging there, frozen. Looking ahead, it does not look good. Oh dear. The ideas of aerodynamics wouldn't apply here. Normally, air would flow around anything moving through it, but the air molecules in front of this ball wouldn't have time to be jostled out of the way. The ball would smack into them so hard that the atoms in the air molecules would actually fuse with the atoms in the ball's surface. Each collision would release a burst of gamma rays and scattered particles. And there's a footnote. After I initially published this article, MIT physicist Hans Winternecht contacted me to say that he'd simulated this scenario on their lab's computers. That's so cool. He found that early in the ball's flight, most of the air molecules were actually moving too quickly to cause fusion and would pass right through the ball, heating it more slowly and uniformly than my original article described. Okay, so he's kind of had a little bit of a correction, but that's fine. We continue. And we have little diagrams here. Here's the ball. Here's the fusion zone, where nitrogen and oxygen from the air fuse with the carbon, hydrogen, etc. in the ball. And then behind it, it's leaving behind a near vacuum. Air plus ball equals fusion. These gamma rays and debris would expand outward in a bubble centered on the pitcher's mound. They would start to tear apart the molecules in the air, ripping the electrons from the nuclei and turning the air in the stadium into an expanding bubble of incandescent plasma. The wall of this bubble would approach the batter at about the speed of light, only slightly ahead of the ball itself. The constant fusion at the front of the ball would push back on it, slowing it down, as if the ball were a rocket flying tail first while firing its engines. Unfortunately, the ball would be going so fast that even the tremendous force from this ongoing thermonuclear explosion would barely slow it down at all. It would, however, start to eat away at the surface, blasting tiny fragments of the ball in all directions. These fragments would be going so fast that when they hit air molecules, they would trigger 2 or 3 more rounds of fusion. After about 70 nanoseconds, the ball would arrive at home plate. The batter wouldn't even have seen the pitcher let go of the ball, since the light carrying that information would arrive at about the same time the ball would. Collisions with the air would have eaten the ball away almost completely, and it would now be a bullet-shaped cloud of expanding plasma, mainly carbon, oxygen, hydrogen, and nitrogen, ramming into the air and triggering more fusion as it went. The shell of X-rays would hit the batter first, and a handful of nanoseconds later, the debris cloud would hit. So here we go. Here's the diagram. The time at 30 nanoseconds, we have this plasmized air with an X-ray front, a developing fireball. The ball itself, which at this point, as he described, would essentially be a ball of plasma itself. The poor disintegrating pitcher, who unknowingly brought this on the world, and a poor unsuspecting batter who has no idea what's about to hit him. When it would reach home plate, the center of the cloud would still be moving at an appreciable fraction of the speed of light. It would hit the bat first, but then the batter, plate, and catcher would all be scooped up and carried backward through the backstop as they disintegrated. The shell of X-rays and superheated plasma would expand outward and upward, swallowing the backstop, both teams, the stands, and the surrounding neighborhood, all in the first microsecond. Suppose you're watching from a hilltop outside the city. The first thing you would see would be a blinding light, far outshining the sun. This would gradually fade over the course of a few seconds, and a growing fireball would rise into a mushroom cloud. Then, with a great roar, the blast wave would arrive, tearing up trees and shredding houses. Everything within roughly a mile of the park would be leveled, and a firestorm would engulf the surrounding city. The baseball diamond, now a sizable crater, would be centered a few hundred feet behind the former location of the backstop. Oh dear, here's the city, and here's the, mushroom cloud. Oh dear. Major League Baseball Rule 608B suggests that in this situation, the batter would be considered hit by pitch and would be eligible to advance to first base. Oh, that was catastrophic. The spent fuel pool. Question: what if I took a swim in a typical spent nuclear fuel pool? Would I need to dive to actually experience a fatal amount of radiation? How long could I stay safely at the surface? From Jonathan Bastian Filiatrolt. The answer, which again I feel like in a lot of these questions the answer is nothing good. But let's see. The answer. Assuming you're a reasonably good swimmer, you could probably survive treading water from anywhere to 10 to 40 hours. Okay, he's not really, okay. I see what he's doing. At that point, you would black out from fatigue and drown. This is also true for a pool without nuclear fuel in the bottom. Spent fuel from nuclear reactors is highly radioactive. Water is good for both radiation shielding and cooling, so fuel is stored at the bottom of pools for a couple of decades until it's inert enough to be moved into dry casks. We haven't really agreed on where to put those dry casks yet. One of these days, we should probably figure that out. Here's the geometry of a typical fuel storage pool. So here we are. Got this big pool of water, and we have these storage casks with spent nuclear fuel, and there is some silly person who is already going for a swim without having the question answered. The heat wouldn't be a big problem. The water temperature in a fuel pool can in theory go as high as 50 degrees Celsius, but in practice it's generally between 25 and 35 degrees Celsius. Warmer than most pools, but cooler than a hot tub. That sounds pleasant. The most highly radioactive fuel rods are those recently removed from a reactor. For the kinds of radiation coming off spent nuclear fuel, every 7 centimeters of water cuts the amount of radiation in half. Based on the activity levels provided by Ontario Hydro in this report, this would be the region of danger for fresh fuel rods. So here we are. Back in the pool, it looks like some people are actually pulling up with some like floaties and stuff. So here we go. Here is the radiation zone, and this line indicates fatal in minutes. The second line indicates fatal in hours. And then outside of the third line is a safe dose. And he notes that this water is possibly has less radiation than outside the pool, because you're not only protected from this, but you're also protected from solar radiation. That's interesting. Swimming to the bottom, touching your elbows to a fresh fuel canister, and immediately swimming back up would probably be enough to kill you. Yet, outside the outer boundary, you could swim around as long as you wanted. The dose from the core would be less than the normal background dose you get walking around. In fact, as long as you were underwater, you would be shielded from most of that normal background dose. You may actually receive a lower dose of radiation treading water in a spent fuel pool than walking around on the street. But then, that would be the same if you were in a non-fuel pool. So here we have, again, the diagram with the various lines of fatality, but then these people are safely enjoying a warmer than normal pool. Just don't sink to the bottom. And he notes, remember, I am a cartoonist. If you follow my advice on safety around nuclear materials, you probably deserve whatever happens to you. Little me. That's if everything goes as planned. If there's corrosion in the spent fuel rod casings, there may be some fission products in the water. They do a pretty good job of keeping the water clean, and it wouldn't hurt you to swim in it, but it's radioactive enough that it wouldn't be legal to sell it as bottled water. And he notes, that's too bad. It didn't make a hell of an energy drink. Wasn't there a period of time in the early 20th century after radiation was discovered where it was believed to be, like this miracle product that could potentially heal you? They thought radiation was good. And I mean, like, obviously we know now that there are particular situations where it can be, like in radiation treatment. But those are, highly contained, standardized experiences. You can't just stand next to some uranium and have your eczema clear up. So that's something we know now. But that sounds like something that people from that time period would really go for. Some water with radioactive fission remnants left in it. We know that spent fuel pools can be safe to swim in because they're routinely serviced by human divers. However, these divers have to be careful, I bet. On August 31st, 2010, a diver was servicing the spent fuel pool at the Leibstadt nuclear reactor in Switzerland. He spotted an unidentified length of tubing on the bottom of the pool and radioed his supervisor to ask what to do. He was told to put it in his tool basket, which he did. Due to the bubble noise in the pool, he didn't hear his radiation alarm. When the tool basket was lifted from the water, the room's radiation alarms went off. The basket was dropped back in the water, and the diver left the pool. The diver's dosimeter badges showed that he'd received a higher than normal whole body dose, and the dose in his right hand was extremely high. The object turned out to be protective tubing from a radiation monitor in the reactor core, made highly radioactive by neutron flux. It had been accidentally sheared off while a capsule was being closed in 2006. It sank to a remote corner of the pool, where it sat unnoticed for 4 years. The tubing was so radioactive that if he'd tucked it into a tool belt or shoulder bag, where it sat close to his body, he could have been killed. As it was, the water protected him, and only his hand, a body part more resistant to radiation than the delicate internal organs, received a heavy dose. Oh gosh, this kind of depicts him carrying it. I hope he got to keep his hand. Jeez, oh man. So, as far as swimming safety goes, the bottom line is that you'd probably be okay as long as you didn't dive to the bottom or pick up anything strange. But just to be sure, I got in touch with a friend of mine who works at a research reactor, and I asked him what he thought would happen to someone who tried to swim in their radiation containment pool. In our reactor? He thought about it for a moment. You die pretty quickly before reaching the water from gunshot wounds. Not allowed there. Now let's see. I think these are a series of... Okay. This here, these two are a couple of quick answers. Let's do these quick. These are weird and worrying questions from the What If inbox, number 1. So he has kind of a spattering of these quick answers throughout the book. Question. Would it be possible to get your teeth to such a cold temperature that they would shatter upon drinking a hot cup of coffee? From Shelby Everett. He answers, thank you, Shelby, for my new recurring nightmare. Oh my god, why would you even think of that? Also, I doubt it. I feel like if you could get your teeth to such a cold temperature that this temperature reaction would possibly happen, that they would have already shattered. You know, I don't know. That just doesn't seem right. But also, I don't want to think about it, and I'm sorry for making you think about it. Your teeth are fine. Everything is fine. Don't worry. And then a question. How many houses are burned down in the United States every year? What would be the easiest way to increase that number by a significant amount? Say at least 15%. From Anonymous. And he responds, hello, please. I have this website where people submit questions. Oh dear. That's very concerning. A little preview for next time. In any case, I hope that you enjoyed this trip through the first couple answers of What If. I hope you found it relaxing, possibly fun, and I hope you know that you deserve to have a nice rest of your day, and good sleep if you are watching this at night. I think that's something I want to develop into an end-of-video message, which is the message that, even though I obviously don't know exactly who you are, I can't, that I can tell you that you deserve good things, and to have a nice day, and to have possibly a better day if you've been having a bad one, or a bad week, bad month, bad year. It's been rough recently, I know, for a lot of people, but you deserve to have a better life, a good life, as long as you are someone who, at least at the bare minimum, isn't a jerk. If you look inward and you say, well, I hope I'm not a jerk, I don't really know, I do my best, congratulations, you're not a jerk. I think that 95% of all people are at least okay. I know that some people have a little bit more misanthropy than that, but I think that hating people is boring, and it's more fun to believe in people and to recognize that most people are at least okay. And you, I'm sure, are at least okay. So you deserve to have a good rest of your day and night. In fact, I'm sure if you're watching this, you're better than okay. Even if you don't really feel like it right now. And with that said, I hope you had a nice relaxing time with this video. And I hope to see you next time